Hello, everybody. We are going to continue our topic on hydrology and open channel flow. And today we're going to talk about non-rectangular channels. So far, our focus has been rectangular channels, which in section look like this. Basically, if you're looking, cut a section in the open channel and look into the channel, let's say look downstream, because that's the kind of general guide that we follow. It looks rectangular. If the water level is here, the two characteristics of the flow in section are the depth, Y, and the width of the channel, typically capital B. The question now is, what if the channel section is non-rectangular? It could be any shape, including an irregular channel. I might look like this. How do we deal with these type of sections, and how do we use the ideas that we've learned so far and apply them to a section that looks like this? So that will be our focus today. If you look at the plan view, so this is plan. Here, this is plan. Plan view of any open channel, in particular natural streams, rivers, they're typically irregular. So if you look in plan, that's the top one. And if you cut a section, let's say here, section AA, your section AA, and you look at it, it might look like something what we have down here, which is a cross section of this channel. Now, you will notice a few things in this section. The first one is that the depth varies from one side to another one, and in natural streams you could have different shapes in terms of the section. Sometimes you see streams that have relatively deep, almost V-shaped section. They almost look like this. So that's a section. Typically in steep, mountainous type areas, rivers look like this. They're a little bit simpler in geometry, almost V-shaped, relatively deep, relatively narrow. That's a characteristic of mountainous, steep, natural streams. Sometimes it's actually pretty flat, pretty wide, looks like this. So that's a section. And it is, as you notice, it's made of a few components in the flow. When you have a relatively low flow, water level might be in here, and only the deeper portion of the channel will be active. And then as the water level goes up, let's say you have a flood, water level might be up here now, and then you have a much wider flow area in section. This is typical of relatively mild slopes that have a relatively mild slope in the longitudinal direction, and they're much wider in section compared to steep channels. Now, if you look at the section at the bottom, this one only shows one side, the deep side of the channel, and then one shallow side on one side. Now, as we said, at low flows, we have water levels somewhere here. And typically, we call this section of the channel the main channel. This is the deeper part. This is the part that's typically narrower in plan and active for most flows, including low flows. And then as the water level goes up, so this will be, let me actually write it here. This will be our relatively low discharge. And as the water level goes up, we might get to a high discharge where the water level is higher, and then we get a much bigger footprint at conveying flow. This part of the channel, we call it the floodplain. So this will be the floodplain. Floodplain because typically it's active during flood events when high flows, relatively large discharges. And in some cases, including the Fraser actually, the floodplains could be very wide. And in some cases, there might be infrastructure, even buildings, infrastructure in these floodplains, and you know, at least historic floodplains and so on. So they are part of the channel in a way, but they're also kind of sensitive areas in terms of interaction with the flow and so on. And in many cases, we see some infrastructure built to contain the flow in the main channel and minimize or sometimes eliminate floodplain. For example, we built almost a wall here, let's call it a wall, to block the flow into the flood channel, floodplain, and we call it a dike. Again, this is something we see a lot along the Fraser. Part of the areas where now we see infrastructure, including buildings, they used to be the historic floodplain, but by building dikes, we're managing and controlling high flows in the river and containing it to a smaller footprint. And then obviously water cannot get into behind the dike, and kind of we have the floodplain available as an inactive kind of area. So the point here is that we're looking at relatively complicated geometries, and unlike the rectangular shape that we had before, the area and other characteristics of the flow are not just depth and width. There's more, and there's more parameters used to define them. Now, one more thing about this section is that in practice, in the natural systems, we typically have an irregular section, like the one on the left. Regular because it doesn't really follow a kind of a well-defined geometric shape. It's irregular. Depth is changing from one side to the other one, and yeah, almost randomly. And in reality, in practice, a lot of the time, the channels that are built for practical purposes are trapezoidal, like the one we have on the right. So they're very common. They give us a decent area, cross-section area, and they're, from a construction standpoint, they're not too bad. They don't have vertical walls like rectangular channels. If you remember, our rectangular channels look like this, which could be a little bit of a construction challenge because obviously natural material, gravel and sand and so on, you can't really put them in a vertical wall. So this has to be engineered concrete or so on. But the trapezoidal channel, you can actually have a side slope. It's called a side slope. And that way you can actually have, let's say, natural material, gravel, sand, whatever it is, and have them on that slope. So we call this one the side slope, which is not 90-degree, unlike the rectangular channel. Now, if you look at the rectangular channel, now we have the invert, the width at the bottom of the channel, small b. We have the width at the top of the channel, capital B. We have the side slope. Side slope is typically written in different forms, sometimes as the angle theta, but very common is horizontal to vertical distance, m to 1. So m is the horizontal distance here, and 1 is the vertical. Typically, let's say 2 to 1, 3 to 1, and so on. So it's the horizontal distance to vertical distance. Again, this helps us define the cross-section of the flow in this type of flow. Now, how do we define, and what are the parameters used to define different shapes for a cross-section? I have a summary table here that kind of goes through all of these and defines them. So starting from the top, we have rectangular section. That's the one we have been looking at. And we have the width, b, small b, and we have the depth, y. It's using capital T for width, but it's equal to capital B, or different letters used, but the idea is the same. So I'm going to write it here to see that the width is the same as capital B. So rectangular channels or rectangular shapes, there are a couple of things used to define the shape. The first one is area, very easy. Depth multiplied by width, b times y. And that's very straightforward. Then we have the wetted perimeter. So I'm going to start writing them here. So A is area. This is area, the first column. Then we have the wetted perimeter. Perimeter. Typically, we use capital P to represent wetted perimeter. And what is this? This is the portion of the perimeter of the section that is in contact with the flow. So I'm going to write it here. Portion of perimeter in contact with flow. As the term suggests, the wet part of the perimeter. So what does it mean? Let me show you in a trapezoidal section. So if this is our trapezoidal channel, and if this is the, let's say this is the depth, the wetted perimeter will be this side slope, is part of the side slope, this part of the side slope on the left, and the invert. So this will be P. Okay, so easy to visualize. In case of a rectangular channel, it's the width, B, plus depth, but we have it on both sides, so plus 2y. All right, so that's a straightforward. The next parameter is the hydraulic radius. Hydraulic radius. We need these to define hydraulic characteristics of these channels. That's why we're going through them. Typically, we use capital R to define hydraulic radius, and it's a simple definition. It's equal to area divided by wetted perimeter. So it's really a definition. It's not really a direct geometric dimension. It's the ratio of area to wetted perimeter. Then we have the top width. Top width. Again, typically we use capital T, or sometimes capital B, depending on the reference, but the idea is the same. And this is width at water surface. Okay, so for us in this section that I have at the bottom, the trapezoidal one, this will be P or B, the top width. In case of a rectangular channel, it should be obvious that it's the same as the width of the channel because the walls are vertical. All right. So that's top width. Next, we have the hydraulic depth. So hydraulic depth. Typically, we use capital D to show hydraulic depth. And it is equal to area divided by top width. Again, kind of a mathematical definition, not a direct dimension. What does it mean? If you, again, visualize a trapezoidal channel, let's say it looks like this, and the water level is, let's say, here, right? And we have a width of T, top width of T, right? If you take the area of the flow, which will be this area, and divide it by the top width, you get a depth, which is going to look like this. So I'm going to exaggerate a little bit, but this will be the same. And the depth here will be D, hydraulic depth. Now, if you think about it, what does it mean? It means for a given channel, which has a top width of T, what depth gives me a rectangular, equivalent rectangular shape that has the same area as my actual non-rectangular channel. That's what it means. The orange area in my sketch is the same as is equal to the blue area. At least I tried to show it the same as the blue area. And that is defined by D. In other words, it says, if I want to replace my non-rectangular channel with a rectangular one, what is the depth of that rectangular channel? What is the equivalent depth? So it's a definition. It's not a physical dimension. Very important to remember, all these variables that we're talking about, they're dependent on flow. So we shouldn't forget that. I'm going to write it here with a star. All these parameters depend on flow, which is discharge. It should be obvious because we have depth. So depth is dependent on discharge. So if depth changes, all these parameters will change. Now the table, I know it's a little bit small, but the table summarizes these parameters: area, wetted perimeter, hydraulic radius, top width, and hydraulic depth for rectangular channel, relatively simple, trapezoidal, triangular, and circular channel. Circular, a little bit more complicated because it has angle in there, but the idea is the same. So for all of them, we have the same kind of parameters. So unlike the rectangular channel, we need a little bit more information to define the geometry of a non-rectangular channel. And depending on the shape, the equations used for these parameters will be slightly different. Okay, so keep that in mind. Now we're going to go to our specific energy idea and see how we can translate this to the specific energy idea to non-rectangular channel. So what we have on the screen is a typical non-rectangular channel. Let's say it's a natural irregular channel. It has a top width of B, area is A, and depth is Y. Now, if you remember, for a rectangular channel, which looks like this, if the depth is, if the water surface is here, we have a depth of Y and a top width of B, which is the same as the width of the channel itself. And the specific energy was defined as E pressure head plus velocity head, V squared over 2G. And if we convert this to depth for pressure head and use discharge to define velocity, unit discharge, Q squared over 2G Y squared. That was a typical specific energy equation for rectangular channels. And we also know that by definition, small q unit discharge is equal to capital Q total discharge divided by width of the channel. Okay. Now let's go to a non-rectangular channel and see how we can translate things. So specific energy was pressure head plus velocity head. Nothing new. This is the same. Doesn't matter what the shape is. It's always the combination of these two. Now, if you have hydrostatic pressure, P over gamma is the same, is depth, a representative depth, plus, for discharge, I can't really use this small q anymore because it's not rectangular. The unit discharge doesn't really mean anything here if it's non-rectangular. So I'm going to switch to capital Q. I'm going to say capital Q squared over 2G. But remember, we had Y squared. And now we're replacing small q with capital Q. So B squared also shows up. And B times Y is going to be area. So we're going to say area squared. So kind of a translation of the equation into a more general form. If you take this and simplify it for a rectangular channel, we go back to what we have for the rectangular channel in terms of small q. So nothing new, but it's just generalized. And we already know that this, velocity is q divided by a. So that's how we got here. And this will be an cross-sectionally average velocity. So it's average over the cross-section of the flow. Now, one challenge here, and you might be thinking about it already, is that, okay, we're taking an irregular section with velocity with an average velocity, but depth and velocity change across this section. Unlike a rectangular channel, the geometry is changing, so velocity will probably change too, and that is correct. So how do we deal with that? So in our equation, we're not going to change anything. We're going to say, okay, we're using an average velocity, but actual velocity may not be just the average discharge divided by area. So how do we take that into account? We do that by a simple approach, and we're just going to say, let's not change the equations, but add a correction factor. Let's add an alpha here and call this alpha parameter, call it the velocity correction coefficient. Velocity correction coefficient. So what are we doing? We're saying let's continue to use an average, cross-sectionally average velocity, but the velocity, the actual velocity is not really the same across the section because everything is really changing. So how do we account for that? We just add a correction factor called alpha, and it's just a number added as correction to the velocity term, right? So our specific energy equation will look like this. And the only really difference that we've added is the addition of the correction for velocity. In here, A is area, and keep in mind, it is a function of depth. It depends on depth, obviously. And we have a correction for velocity. We call it the Coriolis coefficient or velocity correction coefficient, alpha. Why do we have it? Because velocity is not uniform across the section, across the cross section. So we need, but we're using Q over A. So we have just one velocity, but it's not the same everywhere. It's different. That's why we're dealing with, we're adding this coefficient. What is this coefficient and how do we calculate it? So if you imagine you have a section and it looks like this, right? That's a section of the flow, irregular section. And we have the water level here. And we have a bunch of points here, everywhere. And each of these will have a velocity. And what we know is that what the equation, the top equation shows here is that if you average velocity heads, so v squared over 2g for all these points, and then average it, the bar means average, that is not equal to the average velocity squared over 2g. In other words, if you, I'm going to write it here, if you average velocity, so you say, okay, VIs, add them up, sigma VI, divide by n, and then square this and divide it by 2g. That's what it means. So all the velocities, average them, and then convert them to velocity head. This is not equal to averaging velocity heads. So sigma VI squared over 2g, and then average it divided by n. These two are not equal. Because of that, we need a correction. So if you take this into account and convert just to the sigma or integral, the same idea, you get the equation for the Coriolis coefficient or the velocity correction coefficient alpha, which will be integral v squared dA divided by v cubed, divided by v bar cubed times a. So it's like a spatial average, weighted average of velocity. It's an indication or kind of a number showing how velocities scattered in your section. And in our class here, we're going to assume alpha is 1, unless otherwise mentioned. I'm going to write it here. Unless otherwise mentioned. So if it's a question or project or something, and there's no mention of alpha, the Coriolis coefficient, you can safely assume it's 1. But if it's not, it's going to be given. It's going to tell you, they're going to tell you that alpha is not 1, either calculated or assume alpha is 1.2 or something like that. So you will have it. Okay, so that was our energy equation. We just added alpha to the velocity term. How about other parameters like depth? We're going to sketch a tiny rectangular channel here. Just a reminder. So if we have a depth of y in a rectangular channel, the fruit number, Fr, was simply velocity divided by square root of gy. How about a non-rectangular channel? So in non-rectangular channel, this is what we're going to do. We're going to use the same equation, but we're going to say, okay, instead of having depth, because depth in a non-rectangular channel changes from one side to another. What is it? Another parameter that's simple and kind of comparable to depth in a rectangular channel? And the answer is yes. We just looked at it. What if we take the section and find the depth of a rectangular channel that is comparable to or is equal in area to our actual channel, but is rectangular, right? So, and that would be equal to area, the hydraulic depth, which is equal to area divided by top width. So let's use that as depth in our fruit number. So we're really using a simplified approach, right? So if we do that, we're going to get this. So we're going to have velocity divided by square root of GD. And D here is hydraulic depth. And then you're gonna have the same issue with velocity. Velocity is not uniform across the entire section. So what velocity are we going to use? The cross-sectional, the average velocity? Okay, sure, that's good, but that's not necessarily equal to the average velocity. So how do we correct that? I'm not showing the math here, but if you do the math, you're going to see that alpha shows up again, but now the square root of alpha. So we're going to take that and multiply by the square root of alpha. And that is going to be our corrected fruit number for a non-rectangular channel. So what we do is we replace depth with hydraulic depth, and then we correct things because of velocity distribution using the square root of alpha. Alpha is the Coriolis equation. Okay, this alpha that we're looking at, what is the range? What kind of numbers we're looking at? So if we have an absolutely uniform velocity distribution, uniform velocity, meaning that velocity at any point in the section is equal to the cross-sectionally average velocity, then alpha will be 1. But if it's not, alpha will be something else. And typically, these are just examples, but for the trapezoidal channel, the type of numbers that we're looking at, this left image is showing velocity contours. It could be somewhere around 1.1, 1.2, somewhere around there. So that's a kind of magnitude of alpha that we're looking at. In natural rivers, obviously, the non-uniformity of the velocity is much higher. So we have velocity ranging quite a bit, changing quite a bit in a section. So alpha will be bigger, and it could be somewhere around 2. So 2 is a relatively large value for alpha. So you keep that in mind in terms of the range. 2 is pretty high for alpha. And yeah, and if you have perfectly uniform, obviously it will be 1. Okay, so that's velocity and specific energy. How about specific momentum? So very quickly, for a specific momentum for rectangular channels, again, I'm going to sketch one here very quickly. If you have a rectangular channel, and water level is here, and depth is this much, y, and width of the channel is b. We saw before that specific momentum m was equal to q squared, small q squared gy plus y squared over 2. That was the specific momentum for rectangular channels per unit width. Per unit width. How do I know it's per unit width? See, I have a small q, so it's per unit width. And this was the equation for kind of the specific momentum. If you remember, the terms in our specific momentum, especially the second term here, actually came from the the hydrostatic force. Remember, force was equal to 1/2 of gamma y squared times b in rectangular channels, right? That's kind of a leftover from that hydrostatic force that shows up here. And then once we did the calculations, we had a over b in a rectangular channel, and in the rectangular channel, obviously, a is b times y divided by b, and it will be equal to y. So that was how we got there. In a non-rectangular channel, this is what we're going to do. We're going to say capital M, specific momentum, is equal to the first term. I can't use a small q anymore because this is not rectangular. So I'm going to use capital Q. G is G. G is not going to change in the denominator. Instead of Y is really left over from area. So I'm going to use A, replace it with A. And now I have capital Q and A. And we already know that. I'm going to write it here. Capital Q divided by B gives us small q. That's how we can go back to rectangular. That's the first term. And for the second term, we have the, again, hydrostatic force. And what we'll have is hydrostatic force will be A area, which is in the rectangular channel per unit width is the same as Y. And then the second one, 1/2 of Y, if you think about it, is actually area divided by B, or hydraulic radius. So I'm going to say this is D hydraulic radius. Why is this, and where did we get this from? Again, remember the hydrostatic force. One, we have y squared. One is dimension, is depth, area, multiplied by b gives us area. And the second one is 1/2 of y, which is the centroid, the depth of the centroid. So the first one is A, area. The second one is D, hydraulic radius. So I'm going to highlight this equation that we have. Now, we have the same challenge. We are assuming that the velocity in our non-rectangular channel is uniform, but in reality, it is not. So how do we fix that in the first term where we have discharge? We're going to say, okay, let's not change anything, but multiply by the first term by beta as a correction term and fix things. So if we rewrite our equation, we're going to have specific momentum in a non-rectangular channel is equal to the correction factor beta times q squared GA plus A times hydraulic radius. But let's keep it simple again, keep it one more step simpler. And we're going to replace that hydraulic radius with an average depth, y bar. So what is that? That's an average depth across the non-rectangular channel. Obviously, depth changes, but if I can get an average and use it, that's going to give me a simpler equation. So I'm going to say this is average depth in that non-rectangular channel. Okay, so our non-rectangular specific momentum equation will be, everything has to be in terms of capital Q, obviously. So capital Q divided by A gives us the first term, which is the velocity, comes from velocity, or kinetic energy, I should say. But velocity is not uniform, so we correct it by applying a correction of beta, called beta. And then the second term is the hydrostatic force. And it comes from pressure at the centroid, which is hydraulic radius, or y bar. multiplied by area, which is A. So that would be our specific momentum equation. Now this correction term that we have, beta, is called the Boussinesq equation, or the momentum correction coefficient. So that beta equation term is the same idea as alpha, the Coriolis equation, but this one's for the momentum term, the kinetic energy. Now, if in our class again, these are the equations, and the fact that the flux of the first equation here is telling us that the average of the flux of momentum is not equal to the flux of average velocity. So these two are different, meaning that if I take flux of different points, rho q v of different points, and average them, that will not be equal to rho q times the average of velocity. These will give us different equations. And again, if you do, I'm not going to show you here, but if you do the math, you're going to get an equation for beta, and it will be v squared dA over v bar squared a. We're going to assume in our class, we're going to assume beta is 1 unless otherwise noted. So I'm going to write it here. Unless otherwise mentioned, let's say. Again, if it's a question or a project or something, and there's no mention of the momentum correction coefficient, it's safe to assume it's 1. Otherwise, it's going to be given, and you'll have it. Okay, so let's summarize. So we have the specific momentum equation, specific energy equation. I'm going to write it here. Specific energy. That's the equation we have. Just keep in mind that we're going to add a correction to the velocity term by adding alpha. I'm going to write that discharge divided by A is the average velocity, obviously. Then we have the Froude number. So Froude number FR is this one. Again, we have a correction of square root of alpha. And keep in mind, always, area is a function of depth. It's not a geometric property of the flow. It's a flow property. And then we have the specific momentum. Specific momentum, M, capital M, and it's going to be the equation we have at the bottom, correction of beta applied if needed. And we can simplify it as y bar being equal to A over D, or hydraulic radius. This is through the fact that y bar can be averaged, or it can be approximated as the hydraulic radius, A over B, or D. For simplicity. Okay. Okay, so I just have a quick review of the derivation of these equations. I'm going to go over this very quickly. You can look at it and make sure that you're following how we got there. So we started with the Newton's second law. We know that the resultant force left-hand side is equal to rate of change of momentum, flux of momentum. We're assuming there's no bed shear stress, and the slope is not too much. It's mild slope. And then we just simplify things. Left-hand side is hydrostatic force. Right-hand side is just velocity converted to, or written in terms of discharge. And just rearranging things, nothing new here. And dividing by gamma. So I'm going to write it here. Divide the equation above, divide by gamma to get the momentum per unit weight. So this will be per unit weight of the fluid. You get that equation. So nothing really new. It's the same equation that we had, the same approach, but in a general term. Now, for rectangular channels, just plug in the values for rectangular channel, and we're going to go back to what we already saw for rectangular channel. So in this step, we're again dividing by B. So we get this equation, and this will be for rectangular channel per unit width, because we divided by B, per unit weight, because we already divided by gamma up there, per unit weight. And this is for a rectangular channel. Again, nothing new, just the same the same concept, the same idea. Now, one last thing on this non-rectangular channels is that the idea of a wide channel. So wide channel, I'm going to call it assumption. So what is that? So many channels that we deal with, especially natural ones, are irregular. So they look like this. And the water level is up here. Luckily, in a way, luckily, most of them are pretty wide, meaning that the impacts of the side walls are minimal. So if you look at the irregular channel that we have here, depth might be something like this, and it changes from one side to another one. The top width is B, and it's pretty wide. And we just saw and we just learned that there's an equivalent rectangular shape like this that has a depth of D, hydraulic depth, equal to A divided by B. And if the channel is wide, so I'm going to write it here. If B over Y is large, I'm going to put it in quotation because what does it mean, large? We'll come back and talk about it later. But if the channel is wide, the effects of the side walls are going to be negligible. So we can assume that our channel is, on average, looks like that rectangular green box that we have. Yes, in reality, it's not, but it's pretty wide. The side walls are not doing anything. So I'm going to assume, for simplicity, I'm going to assume that it's just like a rectangular channel. And then look at it as the equivalent shape. So equivalent to this rectangular channel. With a depth of, I'm going to write it here, with a depth of D, D, and a width of B. So what's happening here? First of all, it's an assumption. So we're simplifying things. We're making some assumptions to make things simpler and easier to deal with. We're saying if you have a irregular channel, but the channel is wide, and luckily, many natural channels are like that. The effect of the side channel and that slope on the side is not going to impact the entire flow field. So I can assume it's rectangular, but what depth? I can use a depth that gives me the same area of a rectangular channel equivalent to the area of the original non-rectangular channel. In other words, that's the definition of the hydraulic depth, an area that has a that has a that is depth of D, capital D, which is the hydraulic depth. So this idea helps us a lot to deal with non-rectangular channels in an equivalent way, looking at them as rectangular channels. And obviously, as we saw before, rectangular channels are way simpler, equations are simpler, and so on. So this is an assumption that we'll use, and we'll look at this, what we mean by wide channel. What is the requirement for B over Y being large? We'll look at that later, but that would be an assumption that in some places helps us avoid the more complicated equations we have for non-rectangular channels, and we'll come back and use them.